Mrs. Lilich presents Ingrid's Science Show. This episode, Nuclear. Hello everyone, it's Ingrid here. Today, we'll cover the nuclear stuff in the class. This includes: there are 3 kinds of nuclear reactions. The first of these is nuclear fission. Nuclear fission occurs when a heavy nucleus is split into smaller nuclei, releasing energy in the process. This happens when the nucleus of a material like uranium-235 absorbs an extra neutron. As you can see, the softening causes a chain reaction, which is taking advantage of a nuclear power. The second type is nuclear fusion, where 2 light nuclei fuse at high temperatures. Nuclear fusion occurs naturally in stars, including our Sun. Isotopes of hydrogen are the most common kind of fuel. Here we have deuterium and tritium, 2 of these isotopes. Let's see what happens when we add 1,000,000 degrees Celsius to these 2, similar conditions to the Sun's core. And that, my friends, is where most of the world's natural energy comes from. The third type of reaction is the most common on Earth, nuclear decay. This is better known as radioactivity, where unstable nuclei give off particles until they achieve stability. Like there are 3 kinds of nuclear reactions, there are 3 kinds of nuclear decay. The first is alpha decay, where 2 protons and 2 neutrons are given off. The next is beta decay, where a particle like an electron is given off. And finally, we have gamma radiation, which is the most dangerous of the 3, and cannot occur without one of the other 2 types, seeing as gamma only gives off energy. So how do we go about calculating radioactive decay? I'm glad you asked. I'll show you the 2 kinds of problems you'll encounter. The first of these looks a little something like this. It's easy, really. We just have to think of it algebraically. Subtract 4 from 235 and 2 from 92. Wonderful! Now let's cross-reference the periodic table. Ah! The element that fits the bill is thorium. The other kind of problem deals with half-lives. A half-life is the time it takes a radioactive sample to decay halfway. Scientists measure radioactivity this way due to the unpredictability of it. In any case, there's one tool that's useful in any half-life problem. It's this handy-dandy chart. So, let's see what we have here. Gold-198 has a half-life of 2.7 days. How much of a 96-gram sample would be left after 8.1 days? This chart is useful due to the fact we can find any missing variable. So let's start recording some stuff. The first half-life.